Welcome back, everybody. It is my pleasure to introduce today's speaker. So we have Alexei Stepanenko from Cardiff University. So he's a PhD student here. And he will talk about eigenvalue of Schrodinger operators perturbed by dissipative barriers. So Alexei, the floor is yours.
Thank you, Matteo. So first of all, I'm going to put a link to my website in the chat, and on the website you'll find the slides for the talk. Okay. Okay, so as Matteo said, I'm going to talk about dissipative barriers today. So firstly, I want to thank my supervisors, Jonathan Bernazzi and Marco Marletta, for their guidance and support throughout my PhD so far. So first thing I want to do is indicate the class of objects I'm going to be talking about today. So let T0 be a linear operator. And in this talk, I'm going to be concerned with sequences of operators of the form Tn. So Tn is equal to T0 plus I gamma Sn. Gamma is a fixed positive number. It's sort of a coupling constant. Sn is a sequence of bounded self-adjoint operators, which are compact relative to T0s. And furthermore, Sn tends strongly to the identity operator as n goes to infinity. And so this sequence, I gamma Sn, this is what I'm calling a sequence of dissipative barriers for T0s. So a concrete example of such a sequence of operators is written in equation 2. So in equation 2, T0 is a Schrodinger operator on the half line with a potential Q, and the operators Sn. I'll refer to Sn as the barrier operators often. So the barrier operators for 2 are multiplication operators of a form of a step function of size n. And so what I want to tell you about is a little bit about what happens with eigenvalues of such operators Tn as n goes to infinity. So for large n, so in the example for 2, as n gets large, the support of this step function gets larger and larger. So this talk is based off the preprints at the top of the screen. So it's an archive, and the code is there. The talk will be split into 3 parts. The first part, I'll talk about a dissipative barrier method. This is a technique from numerical analysis, and this is the dissipative barrier method. It motivates the results which I'll talk about in the remainder of the talk. So in part 2, I'll talk about some results for abstract operators, and these are all based off enclosures for the limiting essential spectrum, which I'll also tell you about. And then in the final part of the talk, I'll present more precise results in the more concrete setting of 1D Schrodinger operators. So here I'll have convergence rates, I'll have inclusion results for the essential spectrum, and I'll have more precise characterizations of the sets of spectral pollution. Okay, so first thing I want to do is make sure everyone's on board with what is spectral inclusion and pollution, seen as it is in the title of the preprint. So let H be an operator on a Hilbert space, and let Hn be a sequence of operators on the Hilbert space. And suppose we want to see how and if the spectrum of Hn approximates the spectrum of H. So these notions are useful for that. Hn is said to be spectrally inclusive for H in some set omega if for every number in omega lambda, which is in the spectrum of H, there exists lambda n, which are in the spectrum of Hn, such that lambda n tends to lambda. So in other words, to say that Hn is spectrally inclusive for H in omega is saying that the spectrum of Hn approximates the spectrum of H in omega. The limiting spectrum of H is defined here. So the limiting spectrum of H consists of numbers lambda, for which there exists lambda n, such that each lambda n is in the spectrum of Hn, and lambda n tends to lambda as n goes to infinity. And note that the sequence lambda n need not be indexed by the whole natural numbers, but only by an infinite subset of the natural numbers. So, for instance, I could be the set of even positive integers. So now we're in a position to define spectral pollution. A spectral pollution is defined as the set of points in the limiting spectrum which are not in the spectrum of H. So the limiting spectrum of Hn is essentially the set of limit points for the spectra of Hn. And if the spectrum of Hn accumulates to a point which is not in the spectrum of H, then it's in the spectral pollution. Hn is said to be spectrally exact for H if it's spectrally inclusive for H, and if there's no spectral pollution for Hn with respect to H. So this is essentially saying that the spectrum of Hn reliably approximates the spectrum of H in omega. So final piece of notation, sigma E will denote the essential spectrum, and sigma D will denote eigenvalues of finite multiplicity. And I'm using the Weyl sequence characterization of the essential spectrum. And so for all the operators I'm considering, the spectrum is equal to the union of sigma E and sigma D. Okay. So now consider an operator T0, which is it's a nice operator. It's self-adjoint and it's semi-bounded. And suppose that the essential spectrum of T0 has a band gap structure. So the spectrum of a T0 might look like something as drawn in the picture. The essential spectrum will consist of bands, and in between these bands, in the spectral gaps, there may be eigenvalues. Suppose we want to numerically compute these eigenvalues. Well, what do? You numerically discretize T0. So for instance, using the finite section method or the finite element method, depending on what the operator T0 actually is. Essentially finding a big matrix whose eigenvalues you hope approximates the spectrum of T0. And you'll soon likely run into a problem. While these approximating eigenvalues tend to accumulate very well to the spectrum of T0, although even this can fail, in general, the approximating eigenvalues will approximate points in the spectral gaps which are nowhere near the spectrum of T0. In other words, numerical discretization tends to induce spectral pollution in the gaps. And so there's numerous methods to get around this. And one method is based off sort of preconditioning the operator T0 by adding a dissipative barrier. Right? So dissipative barrier I gamma Sn, where gamma is positive and Sn compact relative to T0, and Sn tends strongly to the identity operator. So these perturbed operators Tn tend strongly to T0 plus I gamma. as n goes to infinity. This is following from the strong convergence of Sn to the identity operator. And this operator T0 plus I gamma, I'll refer to that as the shifted operator. So the spectrum of the shifted operator is exactly the spectrum of T0, shifted up I gamma in the complex plane. So it's an exact copy as shown in the picture. So in particular, the eigenvalues of T0, which we're interested in computing, they're exactly encoded in the eigenvalues of the shifted operator, which I'll sometimes refer to as the shifted eigenvalues. Okay, and so yeah, because of this, it suffices to compute the shifted eigenvalues. Now, let lambda naught be an eigenvalue of T naught. Assume that Tn is spectrally exact for the shifted operator in some open set U of the complex plane. We can reasonably expect this because Tn tends strongly to the shifted operator, and we'll prove results for where such spectral exactness occurs. Assume for simplicity that the only point in the spectrum of the shifted operator that intersects U is exactly this shifted eigenvalue, lambda naught plus I gamma. So we have a situation in the like in the picture, the green region is U, the black dot in U is lambda naught plus I gamma. And Tn is spectrally exact for the shifted operator in the green region. And hence, for large n, Tn will have an eigenvalue, lambda n, near lambda naught plus I gamma. So this lambda n is drawn in red here. And furthermore, from the spectral pollution part of the spectral exactness assumption, all eigenvalues of Tn in this region U will be near the shifted eigenvalue lambda naught plus I gamma. So that's great. We have the eigenvalues of the perturbed operator here exactly approximate lambda naught plus I gamma in the green region. What you then do is numerically compute lambda n. And it turns out, and this is a non-trivial fact, that the eigenvalues of the perturbed operator can be reliably numerically computed. This is due to the T0 compactness of the operators Sn, as well as the fact that T0 are sort of nice operators, they're self-adjoint and they're semi-bounded. And if you want to prove sort of general results of this form, you can use the essential numerical range, which has been recently introduced by Bergley, Marletta, and Tretter. Okay. And so, in order to have any hope of making this sort of method working, we need to know how the spectrum of Tn behaves in relation to the spectrum of the shifted operator. And so that's the question that I'm going to be talking about today. In other words, actually, what we want is spectral inclusion and pollution results for Tn with respect to the shifted operator. So we can say one thing straight away. Since the barrier operators Sn are T0 compact, by Weil's theorem, the essential spectrum of Tn is equal to the essential spectrum of T0. So the dissipative barriers have no effect on the essential spectrum. And since T0 is self-adjoint, the essential spectrum of T0 is contained in the real line. So the perturbed operators The essential spectrum of perturbed operators is exactly this. Hence, the problem reduces to understanding the eigenvalues of the perturbed operators. We can also say something about the spectral pollution of Tn with respect to the shifted operator right off the bat as well. Notice that the spectrum of the shifted operator lies on the line I gamma plus r. So it lies up here. This is nowhere near the essential spectrum of Tn, which lies down here. But Tn is meant to be approximating the shifted operator. Therefore, the essential spectrum of T0 is contained inside the spectral pollution set of Tn with respect to T0 plus I gamma. So we have a picture sort of as shown at the bottom here. The essential spectrum is down here. And at least for certain appropriate Schrodinger operators, we'll show that the spectrum of Tn for large n looks something like this. So it turns out that the spectrum of the shifted operator will be approximated by the eigenvalues, and there can be spectral pollution for Tn other than this sigma e of T0, but it's sort of quite nice. It's quite well behaved in the sense that it's in between these bands. Okay, so now I'm starting the second part of the talk. I'm going to switch formats as well because I couldn't see the time, and now I can see the time. Okay. So now let T0 be a self-adjoint operator. So this is assumption one is my base hypothesis for the abstract theorem I'm going to present. Let T0 be a self-adjoint operator. Let Sn be a sequence of operators tending strongly to the identity operator, such that Sn is bounded. Sn are bounded uniformly in n. So C here is independent of n. As before, define the perturbed operators as T0 plus I gamma Sn. The main tool that I'm going to be utilizing in this part of the talk is the limiting essential spectrum. So limiting essential spectrum is defined here. Let's break that down. It consists of complex numbers lambda, such that there exists a sequence un such that each un is in the domain of Tn. Un is normalized, un is tending weakly to 0, and this norm goes to 0. So un approximately solves Tn minus lambda un equals to 0 as n goes to infinity. And note, just as in the definition of the limiting spectrum, un only needs to be indexed by an infinite subset I of natural numbers. So what can we do? The limiting essential spectrum can define a bad set. So this bad set is the limiting essential spectrum of Tn union the limiting essential spectrum of the adjoints of Tn complex conjugated. So why is this a bad set? That's a bad set because of the following theorem, which is due to Berkeley immediately applied to this setting. Assume assumption 1 holds. Then if lambda is a shifted eigenvalue such that lambda is not in the bad set of Tn, then lambda is approximated by the eigenvalues of Tn. In other words, there exists lambda n, such that each lambda n is an eigenvalue of Tn, and lambda n tends to lambda. Furthermore, the bad set captures all the possible spectral pollution for Tn with respect to the shifted operator. So this is very nice. It captures, it gives us lots of information about the spectral inclusion and all the information about spectral pollution. However, as it stands for these operators Tn, the limit in the central spectrum might be just as hard to compute as the spectrum of Tn itself. So one way to get around this is to find enclosures for the limit in the central spectrum. One such enclosure is the limiting essential numerical range. So the limiting essential numerical range, I believe, was introduced by Sabina Berkeley in her PhD thesis. And it's defined in a somewhat similar way to the limiting essential spectrum, except the norm that was tending to zero is now replaced by this inner product that's tending to zero. The limiting essential numerical range, WETN, is a convex and closed subset of the complex plane. And importantly, the bad set of Tn, which captures all the spectral pollution, is contained inside WETN. Now, this WETN, it turns out, can be computed. And what it looks like is shown in the picture. So the picture assumes that the bands that we're seeing are the smallest two bands. It's assuming that T naught is unbounded from above, but not from below. So yeah, it consists of, it's like the strip, semi-infinite strip with imaginary values between 0 and gamma, and its real values more than the infima of the essential spectrum. However, unfortunately, this is the limiting essential numerical range is not enough. The reason is if a shifted eigenvalue in the spectral gap, so this is one which we want to approximate with Tn, is living up here. It's going to be contained inside WETN, and hence WETN it gives no information on spectral inclusion for these shifted eigenvalues, and it gives no information about spectral pollution in the vicinity of these shifted eigenvalues. Okay. And how do I get around this is to introduce new enclosures for the limiting essential spectrum, which are not convex in general. So this is first theorem. I suppose that assumption 1 holds. We need that the barrier operators satisfy additional assumption. So we assume for theorem 1a that Sn are projection operators for all n. And if this holds, then I can construct this set gamma A such that the bad set containing all the spectral pollution is contained inside gamma A. The definition of gamma A is written out here, but I think it's more instructive to look at the picture. So gamma A, it consists first of all of points in between the essential spectrum and the shifted essential spectrum. As well as this, it contains these sort of caps at the end of the bands. And the boundaries of these caps are exactly semicircles. So an example of barrier operators satisfying this hypothesis of theorem 1a. So of barrier operators, which are also projection operators, in the context of T naught being a Schrodinger operator on the half line, we've already come across. It was these Sn, which were step functions of length n. So that's shown in the picture. And so the question naturally arises, can we construct the barrier operators differently in order to improve this enclosure? And the answer is yes. And this is the assumptions we need. First of all, I require that Sn, they're all positive and they're all bounded. The operator norm is all bounded by 1. Furthermore, I require this weird assumption here. So let's break this down. It's saying that for all sequences un in the domain of T naught, such that un is a bounded sequence in the Hilbert space, and T naught acting on un is also a bounded sequence in the Hilbert space. For all such sequences, this imaginary part of the inner product, Sn un T naught un, that tends to 0. And so if this holds, then I can prove that the bad set of Tn is contained inside an enclosure gamma b, and gamma b just consists of all the points between the essential spectrum and the shifted essential spectrum. So this is not exactly a transparent hypothesis. However, I expect that this sort of condition can be, you can construct such Sn in almost any setting, and in the setting of T naught is a Schrodinger operator on the half line, such Sn look like this, as shown in the picture at the bottom. So Sn are now smooth, and so therefore they take a finite distance in x to go from 1 to 0. And furthermore, as we increase n, this transition distance, it increases, it gets bigger and bigger. So the tail, it gets bigger and bigger, and this Sn is sort of getting stretched out. And with the, so a corollary for these theorems is that if assumption 1 and either one of these hypotheses holds, and we have a shifted eigenvalue, so an eigenvalue of the shifted operator, then there exists an open neighborhood of U of this shifted eigenvalue, such that Tn is spectrally exact for the shifted operator in this open neighborhood U. And so this open neighborhood is actually is defined as any open set which doesn't intersect these enclosures. And so you can see in particular that with the enclosure for the part B of the theorem, your open neighborhood U can be bigger in general. It's worth noting that this sort of corollary for the case of Sn being projection operators has also been proved by Hinchcliffe and Strauss. Okay, so this is very nice. We have these enclosures. Outside of these enclosures, we know that the eigenvalues are approximated, and we know that the spectral pollution is contained inside the enclosures. However, there's still much more to be said. We have no knowledge of the convergence rate for the shifted eigenvalues. We have no knowledge on whether the essential spectrum of the shifted operator is approximated by the eigenvalues of Tn. And we have we don't know what the spectral pollution inside these blue regions might actually look like. And so in order to address this question, these are more precise questions, I'm going to move on to a more concrete setting of 1D Schrodinger operators. Okay, so first let's look at a picture. So numerical illustration. So here, T0 is a Schrodinger with a complex potential. So T0 is non-self-adjoint now. And the complex potential is actually a dissipative barrier itself of size x. The perturbed operators are defined as follow. So here, the dissipative barrier is is a step function of size r. So it's of the projection operator type. The essential spectrum of T0, since this potential here, I chi 0x is in L1, the essential spectrum of T0 is the half-line. Therefore, the essential spectrum of the perturbed operator TR is also the half-line. The essential spectrum of the shifted operator, therefore, is exactly I plus the half-line, so it's the line here. And the region in between the these two, the essential spectra and the shifted essential spectra, we call gamma gamma, and it's shaded in gray. So the blue points, they represent the eigenvalues of the shifted operator. And the orange points, they represent the resonances of the shifted operator. And I'll talk more about them later. The black points are the eigenvalues of the perturbed operators, TR. And the red points is the resonances of TR. And so what we observe is that as we increase R, resonances of TR emerge out of the essential spectrum, the half-line, and they become eigenvalues which, first of all, rapidly converge to the eigenvalues of the shifted operator. And also, they seem here to accumulate to the essential spectrum of the shifted operator. Okay. So in this part of the talk, T0 is going to be a Schrodinger operator on the half-line with a potential Q, possibly complex valued. And T0 is endowed with a Dirichlet boundary condition. The perturbed, we're going to use a step dissipative barrier. So TR is defined as follows. And gamma here can be complex in general. It makes no difference to our analysis. So as many of you will know, the solution space of the Schrodinger equation is a two-dimensional vector space. And that's what makes these operators so nice to work with. And that's what makes, that's why we can get such precise results reasonably easily. Relatively easily. So for many potentials Q, one of these solutions of the Schrodinger equation is exponentially growing, and the other solution is exponentially decaying. So assumption 2 is the main hypothesis, sort of the base hypothesis for this part of the talk, and it's reflecting this fact. So the assumption is that the two solutions, psi plus and minus of the Schrodinger equation, admit the following decomposition. So here, the exponential is getting factored out, and we're left with a remaining factor psi tilde here, and a similar decomposition for the derivative of psi plus and minus. Now, since the imaginary part of k is strictly positive, this e with the exponential with the plus is exponentially decaying, and the exponential with the minus is exponentially growing. And I'm assuming that all these psi tilde functions are bounded with respect to x, and that ensures that the L2 solution psi plus, is going to be exponentially decaying in x. Finally, assume that everything's analytic with respect to the spectral parameter lambda. So this assumption can be easily shown to be satisfied for two classes of potentials. So the first class is for Q in L1, and this follows by the Levinson asymptotic theorem. And the second class is Q eventually real periodic. So Q is real and periodic outside of some compact subset of the half-line. And that follows by an application of Floquet theory. Okay, so now I'm going to fix a sequence of barrier sizes. So let Rn be a sequence of positive numbers such that Rn tends to infinity. In the next couple of slides, I'll introduce a sort of a 1D bad set for the sequence Trn. So this is analogous to the bad set that we saw in part 2 of the talk. And with this 1D bad set, I can prove the following theorem. So suppose that assumption 2, this decomposition holds. Then any eigenvalue lambda of the shifted operator such that lambda is not in this 1D bad set is approximated by the spectrum of Tn with an exponentially fast convergence rate. Furthermore, the spectral pollution of Trn with respect to the shifted operator, it satisfies this. So the spectral pollution is contained inside the sigma E of T naught, as I explained before, union the 1D bad set. So the 1D bad set captures all the spectral pollution outside of sigma E of T naught. It's worth noting that part 1 of this theorem was proved for gamma small enough. In this paper of Marletter and Scheikel. Okay, so that's theorem 2. So what's the general technique to proving this? The general technique is to express the eigenvalues as zeros of analytic functions, and then to apply complex analysis. So a basic example of a correspondence between eigenvalues and zeros is shown in this example here. So if lambda is an eigenvalue of T naught, then psi plus is the unique L2 solution. So then psi plus, the unique L2 solution must be in the linear span of the eigenfunction, and hence it must satisfy the boundary condition at 0. And then if psi plus satisfies this, then psi plus is a L2 solution of the Schrodinger equation with spectral parameter lambda, satisfying the boundary condition. Hence, it's an eigenfunction proving that lambda is an eigenvalue of T naught. And basically, what we can do is derive a similar analytic function for the eigenvalues of TR. So this analytic function is written out here. The precise form perhaps isn't essential to understanding the talk. However, note that everything here is constructed out of psi tilde and k, which are the functions appearing in our decomposition of assumption 2. And all the results I'm going to present utilize this function fr in combination with tools from complex analysis, especially Rouché's theorem. And so in order basically, we need to use the exponential growth. Very roughly, we need to use the exponential growth in the spectral pollution result that I showed of this exponential here. And so the complex numbers lambda, for which A, it gets small for large R, that causes problems. And that's how my 1D bad set is defined. It's defined as a set of numbers lambda outside the essential spectrum and outside the shifted essential spectrum, for which A gets small for large N. Okay, so this is not exactly a transparent definition. However, we have very nice characterizations of this bad set for the two examples of potential satisfying assumption 2. So if Q is in L1, then I know that the 1D bad set is just empty. So what this implies is that the eigenvalues of TRN accumulate to every single point in the spectrum of the shifted operator. It also implies that the spectral pollution of TRN with respect to the shifted operator is exactly sigma E of T naught. So that's very nice. And when Q is eventually real periodic, the situation is slightly more complicated. So say it's eventually periodic with a period A, and Rn, we need to assume that Rn takes this special form. So the gaps between the Rn is A. Then what we can prove is that the bad set consists of isolated points, which can only accumulate to the band ends of either the essential spectrum or the shifted essential spectrum. And the way I do this is to express this 1D bad set as a zeros of a certain analytic function on a branch of a Riemann surface which has branch points at these band ends. And really interestingly, in this setting, I can prove that the 1D bad set is contained inside this abstract limiting essential spectrum, and hence contained inside this abstract bad set of part 2. Okay, so this is the final result I want to present today, and it's about inclusion for the essential spectrum. And to prove an inclusion for the essential spectrum, I require an additional assumption, and this additional assumption ensures that the L2 solution, psi plus, the L2 solution can be analytically continued with respect to the spectral parameter. So here I've got listed 3 conditions, which with standard conditions, which ensure that this holds. Q can be dilation analytic with power decay. Q can satisfy the name mark condition. or Q can be real valued and eventually periodic. Okay. So the zeros of this function psi plus 0 lambda, remember, are the eigenvalues of T naught, while the zeros of the analytic continuation of this function, they're the resonances of T naught. They're called the resonances of T naught. And this definition is needed for my last theorem. So suppose assumption 2 and 3 hold, the decomposition and the analytic continuation. Then if mu is in the interior of the shifted essential spectrum, such that mu is not a resonance of T naught plus I gamma, then mu is approximated by the eigenvalues of TR with a rate 1 over R. And so in particular, since the band ends and the resonances of the shifted operator are isolated points, this actually implies that every point in the central spectrum of T naught plus I gamma is approximated by the eigenvalues of TR. And so to finish off, I'm going to go back to this numerical illustration again and just fix the ideas. And also I can point out that in the final theorem, the resonances of T naught of the T naught plus I gamma, which are embedded in the shifted essential spectrum. So this is the top orange point here is an example of such a resonance. For those kind of resonance, I couldn't prove the convergence rate. And so looking at the numerical illustration, it seems to suggest that there's a reason that I can't prove that convergence rate, is that it really seems that there's something going on and it's actually might be slower. So I think that's all got time for today. So thank you for listening. Okay. I'm glad you could all see me.
Thank you very much for the very nice and clear talk. Are there any questions?
Yes.
Okay, just one thing maybe. Could you go back to slide 11, where the abstract results were? Yeah, this theorem, I was wondering what, so this is abstract and not just for Schrodinger operators. Did I understand correctly?
Yeah, it's the abstract condition is here.
Okay, so what does it mean for Sn to be between 0 and 1?
It means that it's Sn to be greater than equal to 0 means that just positive operators.
Okay.
And Sn to be less than or equal to 1 means that the operator norm is less than or equal to 1. Yeah.
And are you aware of any cases other than Schrodinger operators where this method works?
I think you could probably get it to work for infinite matrices.
Okay, so yeah, like discrete Schrodinger or things like that.
Yeah, discrete Schrodinger operators with a potential which kind of looks similar to what's shown in the picture.
Okay, thank you.
Thank you.
More questions?
Alexei, could you go to slide 18, please?
Yeah.
So this bad 1D set, what I couldn't remember when you were presenting this is whether you actually have examples where either by proof or by strong numerical evidence you can prove that that bad 1D set is actually empty. sorry, is not empty. Sorry.
So I don't have a rigorous proof for this, definitely. However, I've got an extra slide here. I've got this. So what we're looking at here is a finite difference approximation for the for an operator TR. TR is given here, so the potential Q is just periodic. And so what we observe is that eigenvalues are emerging out of the bottom band into the shifted band. They need to do this in order to approximate this shifted band, but they always seem to be staying in this blue region. And so that would imply by Boltzmann-Weierstrass, if that was really true, if they always stayed in the blue region, by Boltzmann-Weierstrass, there must be some spectral pollution somewhere in this blue region.
By Boltzmann-Weierstrass, yeah, okay, yes, yeah. Plus continuity with respect to capital R, I guess.
Yeah, plus continuity with respect to capital R, yeah.
Thanks.
Yeah.
Any further questions, comments? Yeah, please.
So Alex, in this slide, you use the domain truncation, right, to obtain the numerical result here?
Yeah, so it's the domain truncation, finite difference, yeah.
Yeah, 3 different scheme or?
Sorry?
What is the finite difference method?
I think it's just a normal finite difference. It's 3-point, I think it's called 3-point finite difference scheme.
Yeah, okay.
It's like the most basic one.
Yeah, okay. So
Yeah.
one more question about the bad set and all these results. How about if the operator is not 1D Schrodinger? I mean, Laplacian elliptic PDEs. Do you think?
The answer is I don't know, and I think it's that's the open question.
Okay.
I don't know how this would, because when you start to consider partial differential operators, the solution space is no longer finite dimensional, so you're going to have to use a whole different techniques. Instead of Rouché's theorem, you can use like Gerberg's, harder and probably more interesting.
Thank you.
Can I ask a question?
Yes.
In your last slide, you had some convergence rates for 1D Schrodinger operators. Not in that slide. In the
This one.
Yeah, in this one. So, not the next one. The next one, the numerical computations.
Okay, this one. Yeah.
And so I see here you use the hard cutoff characteristic function of 0R. But before, in the second part, you said that if you use the smooth cutoff, then things improve. Have you tried to use smooth cutoffs for these numerical computations?
Yes, I have. So maybe it's I don't have a picture on hand. Maybe I'll upload one to my website at some point. But I can sort of describe what I sort of saw when for this example, I used the smooth cutoff. Here we have eigenvalues emerging out the essential spectrum to the shifted band. So they look like grasshoppers, right? When we have a smooth cutoff, it looks more like a sequence of ants marching towards the shifted band, and they're sort of really sticking to the middle of the band. And there's more and more of these ants as R goes to infinity. Does that sort of I think it'd be, yeah, I have looked at that numerically, but not analytically.
Thank you.
More questions? Doesn't appear to be the case, so let's thank Alexei again for the nice talk.